I'd like to talk about the distinction between Bayesian and frequentist statistics. So this course has mostly a Bayesian approach, but you may have heard that there's kind of a big divide between Bayesian and frequentist statistics, and a lot of kind of controversy and arguments between these two camps of statisticians. So I want to talk about these kind of two philosophies and talk about the differences and why they exist. I'm not going to take a really strong opinion about which one is better, although I'll give you a bit of an opinion towards the end. Most importantly, I think it's important to be able to recognize the difference between these two categories of approaches, because it'll help you understand the decisions that other people make in terms of what methods to use, and help you decide which choices to make as you choose methods for yourself. So Bayesians and frequentists don't disagree at all about the fundamental rules of probability. So all of the math and the identities that we've talked about, they hold regardless of who you're talking to. In particular, Bayes' rule, the thing we've seen and used many times, that is used by both Bayesian and frequentist statistics. Although when I go into Bayesian, you'll see why it plays a very central role for Bayesian approaches. What differs between these approaches and kind of these philosophies is what we mean when we talk about a probability. So a Bayesian interpretation of probability says that when I write probability of x equals 1, that probability represents my personal uncertainty about the world based on the knowledge that I have. So for example, if I see a coin is flipped, but I don't see the outcome, if I say the outcome of that coin is heads, what is the probability, or the outcome of that coin is x, what is the probability that x equals heads? That will be 1/2 for me. That's my uncertainty about the outcome of the coin. Vice versa, if you flip the coin and you can see it, well, at that point, given your knowledge, the probability that x equals heads is 1, the probability that it's tails is 0. So probabilities represent my uncertainty about the world. And I can express uncertainty about everything in the world. For example, what is the probability that eating hamburgers increases my risk of cancer? Well, I can assign some probability to that, maybe, let's say 80%, based on what scientific literature I've read. And as we gain more information, maybe I read more papers, maybe I do some experiments, that probability may change. As I gain some more evidence in favor, maybe it will increase. And if I gain some evidence saying that there's no link, maybe that decreases. So again, probabilities represent my uncertainty about the world, and my probabilities will differ from your probabilities because we have different information. On the other hand, whereas a Bayesian is happy to say, what is the probability that the weight of a coin is 1/2 versus maybe it's a biased coin that has a probability of landing heads other than 1/2. A Bayesian is happy to say, what is the probability that the weight of the coin is 1/2, and put some posterior distribution over the possible weights of the coin. A frequentist would say, no, the coin is either weighted or it's not. There is some true probability of the coin landing heads, and we don't get to put probabilities over that because that's not a repeatable experiment. Now, it would be if we were drawing the coin from maybe some larger bag of coins with different weights in some repeatable way, at least in principle repeatable way. Now, a big advantage of frequentist statistics is that we can all agree about what the probabilities are. I don't have to say in my scientific paper, well, based on all the information I have, I put the probability that, let's say, eating hamburgers increases one's risk of cancer. I put that probability at 90%, and you, though, might have some other information, and you might put it at 20%. So, again, a nice thing about all these frequentist methods is that we can all agree about probabilities, and therefore there's kind of not the level of subjectivity. I'll talk a little bit about that more in a bit. But frequentists still want to do the types of things that we do a lot in this course, like reason about the probabilities or reason about various things that are unknown about the world, like the causes of cancer, or like what is the weight of some coin, and we want to be able to reason about that. So how do we do that? So let's say we have a coin, and let's say its probability of landing heads can either be 0.5 or 0.6. As a Bayesian, we would write the probability of theta, that's the weight of our coin, given all the data we have, let's say multiple coin flips, and based on our probabilistic inference that we've done a lot in this course, we might find that that's some distribution over 0.5 and 0.6. But a frequentist would say, no, you're not allowed to say what is the probability of theta, because again, theta is a real thing that exists in the world, so that's not allowed. Vice versa, a frequentist would say, okay, we're going to take our data and put it through some estimation process, like saying if we see many more heads than tails, then we're going to estimate the coin to be 0.6 versus 0.5. And that's going to give us an estimate of theta hat. And then we get to write expressions that look like this: probability of theta hat given data and the true theta. Note here that the true theta appears in the condition. So we get to reason about what would happen for theta hat for given fixed values of theta. So in frequentist methodologies, you'll see often a lot of reasoning about what is the probability of theta minus theta hat. So of course, we want to choose an estimator such that our estimated theta hat is close to the true theta. And then we can do some reasoning about what is the probability that theta hat falls at some range relative to the true fixed theta that's unknown. A frequentist method that is used all over the place in practice, I'm sure all of you have seen this very many times, is the p-value. So when we're computing p-values, we're trying to reason about something that truly exists or doesn't exist in the world. Let's use the example of let's use smoking. Does smoking increase one's risk of cancer? As a Bayesian, we would say, okay, what is the probability that smoking increases risk of cancer. And we would write something that's just like probability of H0. We're using H0 as a given hypothesis. But again, as a frequentist, we're not allowed to put H0 in the probability because it truly is or isn't. Okay, so again, we have H0 and H1, which are, in some sense, are parameters of the world. What a frequentist does instead is it says, okay, so there are some things that are truly in the world or not. So in this case, this is H0. This is going in the condition of our probability distribution. Then what we're going to do is we're going to find some data. Let's say go and survey a bunch of people and ask them if they smoke and if they got cancer. That's this thing here. And we're going to compute some test statistic that is just some function of D that may be like, what is the correlation between cancer and smoking? And then we're going to find this probability distribution over what is the probability for data sets in general. So we're imagining that that our data set D tilde is drawn from the null hypothesis, in this case, that there's no relationship between smoking and cancer. And we're going to reason about, now of course that's a repeatable hypothesis or a repeatable experiment, because you could imagine surveying a different subset of the population each time. So we can reason about what is the probability for for the case where smoking doesn't cause cancer, that would get a given test statistic. So we're going to get some distribution of test statistics under that hypothesis, and then we can ask how often would we observe a test statistic greater than the one we actually observed. And a p-value is defined as that probability. So one mistake that's made very often in practice is people say something like a p-value is the probability that the null hypothesis is false. Now hopefully you can understand why a frequentist would never say something like that, because again, you're not allowed to say what's the probability of something that truly exists in the world. So a p-value is the probability that we observe a test statistic greater than the one that we actually observed, assuming that our data was drawn from the null hypothesis. Now again, p-values only really make sense in the context of frequentist statistics, because a Bayesian would just write what is the probability of H0. A related frequentist concept is a confidence interval. So we choose a given interval, L and U, as a confidence interval. Let's say we're looking at the weight of a coin, that is somewhere between 0 and 1 probability of landing heads. We're going to put some interval over those probabilities. Let's say we can determine that the coin has, we'd like to determine that the coin has between 0.6 and 0.8 probability of landing heads. So we call this range LU a confidence interval if it's the case that, assuming our data comes from theta, then the probability that L and U are less than and greater than theta respectively is some probability that we control. So note here that the things that have a distribution over them is not theta, because again, we're not allowed to talk about what's the probability of theta, but L and U, because again, L and U are a function of our data, and therefore they're a function of the true theta. So L and U really are, you should think of it as, from a frequentist perspective, as some fixed procedure that takes you from a data set to confidence interval bounds. So L and U are a function that take in data and give you intervals. And we call that a confidence interval if it's the case that whatever theta is, we get confidence intervals that go around the true theta. There's a related topic from a Bayesian perspective called a credible interval. Which is defined as the probability that theta is greater than or equal to L and less than or equal to U given D for some bounds L and U. So note that here we're taking a Bayesian perspective, so theta is the random variable in question. Compared to the confidence interval, note that in the confidence interval, it's L and U that are random variables, theta is fixed. But here in the case of credible interval, we're in a Bayesian perspective, so theta is in front of the condition. It's a random variable that we're reasoning about. So in some sense, a credible interval is a much simpler concept because it's just some way of essentially distilling some full posterior distribution that we might get from asking what is probability of theta given D and just distilling it down into some interval such that the probability is, let's say, equal to 0.95. Now, so just to be clear, a very common mistake that's made is to say, okay, I give you a confidence interval. Let's say for a coin, my confidence interval from some frequentist method is that the bounds are 0.6 and 0.8 for the coin's weight. And you say, what does that mean? And I might mistakenly say that's the probability, or that the probability is 0.95, that the true coin's weight is within that interval, implying that I'm reasoning about what the true weight of the coin is. But again, we're not allowed to do the probability of what is the coin's weight. The thing we're reasoning about here is L and U.